here. So as I mentioned before, the game plan here for our last discussion here is actually I'm going to do with you what I did with the other half of the class and just kind of finish up talking about the last couple of organic groups, just those two couple of groups that basically contain nitrogen. That way, again, everybody's got the same sort of lecture here. Okay, so we pretty much talked about every single organic group except for really two, and they are sort of related to each other in a sense. They are nitrogen containing. So amines here are really have a functional group that contains nitrogen, and it's sort of this group right here as a nitrogen, maybe in a couple of hydrogens. They really are derivatives of something that we've seen earlier on, which is ammonia. Ammonia, which is NH3, which is this guy here. So they're really sort of based off of ammonia. Obviously, they're missing the hydrogen, but they have some similar properties, just like ammonia, which is kind of polar. This could kind of interact and do some hydrogen bonding there with something like water and stuff like that. So here is our nitrogen group. And in this particular case, it's attached to basically three sort of carbons there. Here's our nitrogen group that's actually attached to one carbon. And again, a couple of hydrogens. As we will talk about, we can actually classify amines just like we would classify carbons and how we classified alcohols and so forth. Kind of the same idea. For example, this amine here has connected directly to 1, 2, and 3 carbons, which means it's a tertiary amine. This nitrogen is connected to just 1 carbon, which means it's a primary amine. So much like what we've done with some other sort of organic groups, we could classify amines as primary, secondary, tertiary, really again here based on how many carbon atoms are directly attached to the nitrogen. So again here, the one we just saw, 1 carbon attached, primary. Here, 2 carbons attached, secondary. And obviously here in this guy here, 1, 2, and 3 carbons attached, which would be tertiary. And by the way, I assume you all know this is out of still chapter 14. It's really the last part, chapter 14, that we had left to kind of go with. So in each of these cases, we do see our primary, secondary, and tertiary amine. How we name amines, as you could kind of get a hint down here, is a common way of naming amines, or a common way of naming amines, I guess is a way of saying that, is very much like how we name ethers, where if you remember on the ethers, we kind of went with the oxygen in the middle and what groups were on either side of the oxygen. Here we go to the nitrogen and we kind of look at what type of groups are there, and that is a methyl group. And we simply just put amine at the end of it. So that's methylamine. Here we would go to our nitrogen and we see 1 methyl group, 2 methyl groups. That is the dimethyl, and again, amine. And here we actually have 1, 2, and 3 methyl groups, hence the trimethyl part, and amine at the end of it. So this is sort of the common way of naming amines. Basically, kind of look at the nitrogen, look for any type of alkyl groups, carbon-containing groups to the left, to the right of it, and maybe up and down, and basically put those groups in alphabetical order, regardless of prefix, and just simply put amine at the end of it is a way that you can name these guys. Any questions on that there? And again, that is what we see here. You know, for secondary and tertiary amines, you know, there is sort of another way that we oftentimes will sometimes name it, which is again more the IUPAC way of naming, which is a little bit more advanced, if you will. What you do is you kind of do the same thing, you look for kind of the longest carbon chain, which in this case is methane, either side. And that's kind of your base of the name. You go methane, drop the E and put amine at the end. And then the other group is N-methyl methanamine. You may be wondering what the N is about. The N is about because this group is attached to a nitrogen rather than a carbon. So normally when we have a group attached to a carbon, we give it a number. In this case, the group's attached to the nitrogen, so we actually use N. Same idea here. This would be the kind of the longest carbon chain that would be there. That would be like ethane. I drop the E and put amine at the end of it. And then we have two methyl groups attached. And, you know, if we would do like, say, 1,1 dimethyl, here we would go N. I ran out of room there. We'll go underneath methyl, dimethyl, ethane, amine. So that's the more IUPAC way of naming it. For us, we will go with the more simple and sort of common name is okay for us for amine. So you don't have to do the IUPAC way of naming. We'll do the common name for amines, which again is what we see down here: ethylamine, dimethylamine, and ethyl dimethylamine. So here, alphabetical, as I was saying before, E comes before M. So we do ignore the prefix there. So again, that's why even though the di is there, ignoring the prefix E before M, and that's why it's ethyl dimethylamine. Any questions on that there? All right, so why don't you take a second here and write the common name for each of these and also classify it as primary, secondary, tertiary. See what you come up with. Okay, so let's start with actually the classification. So here we look at the nitrogen, which is our amine group, and we see it is directly attached to just one carbon, which means this should be a primary amine. Here we look at the nitrogen and we see it's attached to 1, 2, and 3 carbons, which means this is a tertiary. So using the common name, we will simply look at this as a group, and that is a 3-carbon group, which is a propyl group. And we would put amine at the end of it. Looking over here, we actually got 3 different groups. Got a methyl, got another methyl. So we got like a dimethyl situation happening. And here we have a ethyl. So this is really our same guy we just looked at. Again, we would go alphabetical E first. So ethyl, dimethyl. And again, we're comparing the M to the E here in terms of alphabetical, and amine. Any question on those 2 names there? So we also have some aromatic amines, and aromatic amines typically will be that historical name that's used a lot, which is our aniline. And as I mentioned before, you know, when we do get a group that's attached to the nitrogen, instead of using a number, so typically numbers are sort of reserved for carbons. And if we have something attached to a nitrogen, that is where we use N instead of numbers. So aniline here is still used as sort of the base of the name, as a sort of the biggest part that has a functional group and the historical name. So when we look at the next guy over, we again see our aniline part here. And obviously that is the base of the name. So in this case, the group is actually attached to the carbon chain. And this would be carbon 1. And you could go either way in this case, 2, 3, or 4. And if you went the other way, 2, 3, or 4. So what we do here is use a number because the group's attached to a carbon, and that is 4 bromol aniline in this particular case. Now, if we take a look at this last guy, you may be going, hey, there's just a line. Remember, a line sort of in organic chemistry usually means that there is a carbon and a methyl group at the end of it. Here again, we do see our aniline part, which is here. again, making the base of the name. And in this particular case, though, our group that's attached, which is our methyl group, is not attached to the carbon, is actually again attached to the nitrogen. So that is why we use the N here to say that that group is attached to the nitrogen, and it is obviously a methyl group here. So that would be N-methylamine. Any questions on that there? Now, if we wanted to, do a classification, this would be a primary, right? As is one carbon. This guy would be one carbon there and one carbon there. This would be a secondary amine in this case. Any questions on that there? All right, so let's take a look at a couple here. For each of them, write the common name that you would have. So take a second or two. Okay, so let's take a look at this one here. This, by the way, is a tertiary amine, 3 carbons attached. We're going to look at our groups here. So that is a methyl group. We have a ethyl group. And we have another ethyl group hanging out over there. So that obviously is 2 ethyl groups. So that is a diethyl. And then we have a methyl. And then we have an amine. Here again, alphabetical E before M. Again, ignoring the prefix, still just looking at our actual groups attached. Any questions on that one there? This one here is a secondary amine. Again, it's got 2 carbons attached to the nitrogen. In this case, if we kind of look at this side of it, that is our historical name of aniline. Here we have a ethyl group hanging off. Again, here in this particular case, not a carbon, but it is hanging off the nitrogen. So again, this is where we would do our N-ethyl aniline. Any questions on that there, or those two? Obviously, we could draw these guys in line structure as well. And we do get our primary here. Remember that each of these guys are carbons. So that really is 1 carbon attached to the nitrogen, hence the primary. Here we have a carbon there and a carbon there. So that is 2 carbons attached to it, which would be ethyl propylamine. And in this case, 1 carbon, again, at the end of the line would be a carbon, and 1 more carbon there would be our tertiary. This is a 1,2 carbon group, 1,2 carbon group, which is the diethyl. And again, this one line would be the methyl. Same thing here. This is a 1, 2, 3 carbon group, which is our propyl. And this is a 1, 2 carbon group, which is our ethyl. And lastly here, 1, 2, 3, which is our propyl. Any question on those there? Now, amines, because they're really derivatives of ammonia, and ammonia can do hydrogen bonding. Remember that in order to do hydrogen bonding, you do need basically a bond between hydrogen and one of our really electronegative guys, our nitrogen, oxygen, or fluorine in this case. So in this particular case, an amine that does have a nitrogen, where the nitrogen is actually more negative and the hydrogen is more positive, is actually able to bond, for example, with something like water and do a little hydrogen bonding action sort of happening. So because of that, it can be very soluble in water. Same sort of limitations as with most organic things. As long as we got a little less than 6 carbons, you're going to be okay in terms of the solubility with water. But again, as we've talked about a number of times in organic chemistry, as you build out more carbons and hydrogens, as the nonpolar part gets larger, so above 6 carbons involved, the solubility starts to decrease a lot at that point. And again, it's because that nonpolar part pretty much gets in the way of the ability of, say, the amine to hydrogen bond with something like water, So the solubility really does decrease. Tertiary amines cannot hydrogen bond, can form hydrogen bonds only with water molecules. They really can't hydrogen bond to themselves because they lack it. So what that means is, if we take a primary amine, we got something that looks like this. This guy can hydrogen bond actually with itself and water. A secondary, which kind of looks like this, can also do some hydrogen bonding with itself and water. A tertiary amine looks like this, which means it doesn't have a hydrogen, which means it cannot hydrogen bond with itself. But if a water came along, it definitely could do some hydrogen bonding between the water and the nitrogen there. But again, it cannot hydrogen bond with itself like a primary or secondary amine is able to hydrogen bond with itself. For example, if we had two primary amines hanging out there, again, negative, positive, we could do some hydrogen bonding with itself and something like water. But again, because the tertiary lacks that hydrogen, its only sort of form of ability to hydrogen bond would be with water, which again makes it relatively soluble. But it also has a lot of carbons to begin with, so it gets a little bit in the way at some point. Because amines do contain that polar NH bond, they do form hydrogen bonds with water. Our primary can form more hydrogen bonds than our secondary, and our tertiary doesn't have hydrogens on nitrogen. So again, it can only hydrogen bond with water from its nitrogen atom. So like alcohols and smaller amines, including tertiary ones, are soluble in water because they have that ability to hydrogen bond. That's pretty much your basic. Why is something soluble in water? Is probably because they have the ability to hydrogen bond with water. And as we talked about a number of times throughout the sort of semester, pretty much like dissolved like. So things that have similar intermolecular forces are going to be very soluble in one another because they're going to be able to interact with one another the same way they would interact with themselves. So that makes them very soluble in each other. And again, because we have these smaller amines, primary, secondary, and tertiary, that has the ability to hydrogen bond with something like water, that's going to make them relatively soluble, again, with obviously the normal limitation like we just talked about of if you got a lot of carbons involved, going to super limit the solubility of it in water. Any questions on that there? So again, with more than 6 carbons, that hydrogen bonding ability definitely diminishes. So, something like this, which obviously has more than 6 carbons, it's a tertiary amine. Remember, in order for this guy to interact with water, it's got to kind of get to this spot. But now you got this non-polar guy, which doesn't like water. You got this giant guy over here, which doesn't like water. You got this giant guy over here, which really doesn't like water. You got a lot of non-polar parts. You can almost see by me kind of boxing it, it almost like puts this nitrogen in like a little hole. And it's sometimes referred to as steric hindrance, which basically means there's just a lot of stuff in the way. And our poor little water molecule is like, I can't really get in there to interact with it. Got all this stuff sort of in the way. I definitely don't want to interact with any of this part of it. So it really limits the interaction that nitrogen, for example, could have with something like water. The result of that is that we see the solubility really decrease a lot. Any questions on that there? Okay, so I take a second here and decide which of the following compounds should be soluble in water. Primary, secondary, tertiary sort of amine. Here we do have obviously a primary amine. That's definitely less than 6 carbons. So we would predict that it should be soluble in water. It should allow the water to kind of get in there, and it should allow these guys to interact and do some hydrogen bonding. Here we have actually a secondary amine, still under 6 carbons. So again, even though there's a little bit more stuff around, Again, it should still allow that nitrogen. I'll just use the same water to get in there and hydrogen bond with the water. So again, we should expect this guy to be soluble as well. Here we have actually no nitrogens. This is a throwback to the early organic here. This is just an alkane. And this is definitely non-polar, which means this guy is going to want to use dispersion forces. Again, water is going to want to use hydrogen bonding, and that is a recipe for not mixing. And we would expect this guy to be insoluble in water. Any questions on those two? R3. Okay, so amines, because they're also, as I mentioned a number of times, really sort of derivatives of ammonia. You may remember that ammonia is actually a weak base. Ammonia is a weak base, which means when we have amines, they can kind of act really as a base and sort of do our Bronsted-Lowry sort of definition of acid and bases. Remember, our Bronsted-Lowry definition of an acid is a proton donor, and a base is a proton acceptor. And just like what we see here with ammonia and water, water going to donate over the H plus, making water the acid, obviously ammonia the base, making NH4 plus and OH minus. Here, if we look at a primary amine, same sort of deal is going to happen. We're going to get water acting as the acid. It's going to donate up the H plus over to our amine. And really the same thing happens as we talked about with Bronsted-Lowry acid-base pairs. We're going to adjust by a hydrogen and a plus, which means this guy here gains an extra hydrogen, which is why there's 3 of them. This guy here started out as neutral, gained a positive charge, which is why it becomes positively charged. This is what is sometimes referred to as a methylammonium ion. And again, we get kind of like an ionic compound like we do here. This is ammonium hydroxide. And then we obviously have our negative hydroxide that's formed here. That's really why these things act as a base. They form hydroxide is basically your definition of a base. So they definitely will do those reactions, and they form what's sometimes referred to as an ammonium salt, or an amine salt, I'm sorry. An amine salt is formed when the amines, such as those responsible for the really bad, or the odor, I'm sorry, bad, but the odor that you sometimes see in fishes. They're neutralized by acids. Amines react as Bronsted-Lowry bases to neutralize the reaction. So let's take a look at those a little bit closer here. Here is an amine and an acid in this case. So we get really like a acid-base reaction in this case. And if you remember, when we do an acid-base reaction, we basically get 2 things. We get like water and a salt. In this particular case, we're not going to get water because we don't have hydroxide, but we are going to form a salt in this case because our base is lacking hydroxide, so it doesn't have hydroxide. So in this case, what happens is the same thing. The acid is going to donate over its H plus. When it does, kind of like our conjugate acid-base pairs, that is his partner on the other side, which is the Cl minus. Same thing as we saw on the other side. This is our base, which means its sort of conjugate acid part is this guy. And it does, again, gain that charge, and that's sometimes referred to as an amine salt. You don't have to worry about naming the amine salt, but basically in this case, when we take an amine and an acid, we will actually generate a salt being formed as a result of this reaction. Same thing as you see down here with our secondary amine. Again, our acid going to donate. When it does, obviously, it will lose its H plus and make our Cl minus. This guy right here gains the H, as we see, and again gains the plus, again making this amine salt in this case. Any questions on that reaction? So The reaction of an acid and an amine will form basically a salt. And it's really just that transfer of the H plus from the acid really to the base, which is our amine in this case. Any questions on that there? Ammonium salts or amines are usually converted to their ammonium salts, and they can sometimes be used in drugs or medication. So some uses or some of these guys that we do see, like in Sudafed or Benadryl, we do see these ammonium salts being formed. And again, it's really just an amine that has a positive charge with a sort of a counter ion or a spectator ion, like the chloride with a minus charge. We also see it used in some narcotics like cocaine. Again, we see our ammonium salt here being transported into an amine. Some alkaloids are compounds that are produced in plants that do contain these sort of amine groups and these nitrogen groups. Used in anesthetics, antidepressants, and stimulants, nicotine, for example, here. Again, we see sort of our amine group attached. This is actually a tertiary amine, 1 carbon, 2 carbons, and 3 carbons sort of happening in that case. Caffeine's another example here. Again, we see sort of our amine group, same thing, our tertiary amine right there, happening there. Things like morphine as well. Again, our amine group sort of happening over here, codeine and morphine. So if we wanted to draw the condensed structural forms and the line structure, if it's cyclic here for each of these, we would do the same thing that we've done before. Remember, when we have the name, we want to roll backwards in it. So methylpropylamine, when we see the amine, we know that basically that is a nitrogen group, could have some hydrogens or not. So that's a good place actually to start with these, is just to lay up the nitrogen for the amine part. We know that on one side there is a propyl, and also connected in there is a methyl. So we could just kind of connect into our nitrogen what we need. Propyl is 3 carbons, so we would do 3 carbons. Methyl is 1 carbon, and like normal, everything else here would be hydrogen. Now, if you remember though, this nitrogen has a couple of hydrogens. In this case, it would also have a hydrogen attached here. I should have at least 3 sort of bonds to it, and it would look something like this. That would obviously be the condensed formula. If we did our line, it would look something like this. 1, 2, 1 more, there we go, 2, 3, and 1. So it looks something like this. And if you wanted to, you could put the hydrogen in, I suppose. This is aniline, which is again our historical benzene ring, which again, you could just draw with the circle. It also has a nitrogen. And in this particular case, it is 2 chloral. So again, here we actually see a number, which tells us that the chloral group is actually connected to the carbon. That means that this is carbon 1, and you could literally go either way, to the left or the right. I'll go to the right, and that means I would put my chlorine there. That also means that in order to really make this a proper sort of amine group, I do need to add the 2 hydrogens. We really only kind of lose a hydrogen every time we add a bond to carbon. So you can think about it as starting with 2 hydrogens, and then every time you put a carbon bond in there, we lose a hydrogen, and that's why we still had 1 left over here. So we added 1 more carbon bond. We sacrificed the hydrogen in that particular case. Any questions on amines there? Obviously, if the chlorine was attached to the nitrogen, it would be something like N-chloral aniline. And it would look a little bit different again, the main part of it would look the same, but we would have the chlorine attached there. And again, we would have a hydrogen going on as well in that case. So again, that's the difference between N, which means that groups attached to nitrogen, are a number, which means it's attached to the carbon. Any questions on that? Are amines. The last organic group of the season, I guess, is amides. And if it will turn, maybe, here we go. So amides are also nitrogen-containing groups. They're kind of derivatives of carboxylic acids. So carboxylic acids is sort of where they come from. They kind of look like a carboxylic acid, except that they got like an amine group on it. So they got this carbon oxygen double bond with a nitrogen containing group, and that is our functional group for our amides. So for example, here that group is right there. And again, our carbon oxygen double bond with our nitrogen and hydrogen in this case, and that's sort of Tylenol. It contains acetaminophen. And again, here it has an amide group that's attached there. Now, you probably can guess this, and we'll see it here in just a second, but since it kind of looks like a carboxylic acid, but also has an amine, you could probably guess that is pretty much how we make a guy like this, is we take an amine and we take a carboxylic acid and we take out water. So we take out OH and then hydrogen. And that leaves us our NH bond that we see here. So the removal basically of water from a carboxylic acid and an amine when they come together will form an amide. And that's essentially what we see here. Again, going to take out some water. And actually, I'll just turn this guy around so you can kind of see it in the right orientation. So I'm just redrawing like the amine. Or I'm sorry, I'm redrawing the, that's the amide. So when we just, again, we would have an amine here. And again, I'll just draw the amine this way here, whatever it may be. And again, we're going to take out these two guys and stick it together there to make our amide bond, which is obviously our nitrogen and our hydrogen. Here's the sort of idea: carboxylic acid and ammonia, again making our amide, OH and an H. Going to put it together. This is the one I was thinking about. We could go this way. And then basically we just kind of squeeze them together. We have CH3 to CH3. Excuse me. Sorry, CH3, CH3, CH2, CH2. We have our carbon oxygen double bond or carbon oxygen double bond. And obviously we remove the water. So we're going to pick back up here. We have our nitrogen and our hydrogen and our CH3, and then obviously our water that comes off. So basically the removal of water, you push them together, your carboxylic acid and your amine, and you will generate your amide through this reaction. Any questions on that there? So here, if we were going to do this one, again, this is kind of turned the other way. So one more time here, I will draw it and maybe turn it around. There we go. That means I'm going to take out water here. I'll just actually do that. And then pretty much everything stays the same. So I just need to draw my bad benzene ring there. I still have my carbon oxygen double bond. And now obviously I'm skipping this part that I took out. That picks me back up with the actual amide connection, which looks like that. And then we have our CH3. So again, there's our amide bond, basically by squeezing together both sides after you take out water. Questions on that one there? They agree with us, which is good. And again, this is obviously a primary amine. That's a carboxylic acid. All right, so let's talk a little bit about amides and naming. And the answer is yeah, you don't have to worry about naming it. So you don't have to worry about naming amides. In case you're curious, you basically take out the OIC and you put amide at the end of it, or take out the E and put it there. So for example, if you look at going from the carboxylic acid side, there is 1, 2, 3, 4 carbons, which is based off of butane. Drop the E and put amide at the end of it, butanamide. And now connected to our nitrogen, methyl group and methyl group. And that is where the NN dimethyl butanamide comes from. So here, just like we saw with amines, we sometimes will use that N to indicate the connection of the group attached to the nitrogen. Good news is you don't have to worry about naming amides, so let's not worry about it then. So we won't worry about this guy or this guy. We won't worry about that guy. Again, amides in health. Urea is the end product of protein metabolism. It's removed from the blood by kidneys, through sort of dialysis, excreted in urine. And again, here we do see our amide bond in urea, which is one of the products. Some other places that we see these sort of amides, barbiturates as well. We see our bond right there, our amide bond happening. Aspirin substitutes as well. We do see our amide bond right about there. Now, in terms of reactions, amides do go through 2 types of hydrolysis reactions, kind of similar to some of the hydrolysis reactions we talked about earlier on in sort of organic chemistry. One is an acid hydrolysis. And when you do an acid hydrolysis, you actually will get back the carboxylic acid, and you'll get back basically a salt, which again is sort of an ionic compound as a result of it. So a good way to remember it is, if amide goes through an acid hydrolysis, you're going to get a carboxylic acid back. You get the acid back. So acid hydrolysis gets the acid. So if we take a look at the guy that we got down there, we got CH3. Let's try to draw a little bit bigger, I think. Maybe a little easier to see. There's our amide. We're going to add water, and we'll add some HCl and some heat. So what's going to happen is we're really going to pretty much break this amide bond right where it forms. And because this is an acid hydrolysis, hence the HCl, we actually will get back our carboxylic acid. So what is needed to make that a carboxylic acid? We need the OH. So we get this guy here. And again, to complete this into a carboxylic acid from the water, we will generate our carboxylic acid part. So for purpose sake here, we're going to cross that out. Now we can just really count up what's left, and it's going to make a salt. So we're going to get something that going to have some charges associated with it. And we have left over, if we just take the back part of it, nitrogen, 2 hydrogens. We have another hydrogen that will attach onto the nitrogen. So I'll kind of circle it. We have one more hydrogen that will attach on. And that makes like NH4 plus, like ammonium, if you remember that polyatomic ion. And what does that leave? It leaves 1 Cl, which is a chloride. So this is our carboxylic acid, and that is really our salt that is formed. And this is what is referred to as acid hydrolysis. Basically adding water in the presence of the acid will get you back to completed carboxylic acid. Any questions on that one there? Now, the base hydrolysis is a little bit different. During the base hydrolysis, we actually will not get back the carboxylic acid. We actually will make a salt of the carboxylic acid, but we will get back an amine or ammonia depending on sort of what is reacting. So if we take a look at that, which is on the bottom there, getting old to see that thing. So we have CH3. I think it's almost the same one. CH2, C double bond O, nitrogen, and this guy. In this case, we're adding just some sodium hydroxide and a little bit of heat. Now, in the base, we do not get back the actual carboxylic acid. We get basically a salt form of it, but we do get the amine. So in this case, because it's base, we're going to actually start with the amine part. And basically what's left over there on the amine side is this. And to sort of complete this, we need a hydrogen. And the hydrogen comes from the base, and that gets us back our amine. So what's left over? Well, if we look at the carboxylic acid part, we have the carboxylic acid that looks like this. Now, when we look at sodium hydroxide, we could think of sodium hydroxide as H plus and O and A minus. So the H plus I just used over here. So what's left is this oxygen sodium, and it would add to here. And that's really the carboxylic acid salt. It has a negative charge. And to balance it out, there's really a sodium that has a positive charge. And this makes a carboxylic acid salt. Remember, salt's an ionic compound, so that's essentially what we get here. So in the acid hydrolysis, we get the carboxylic acid back. In the base hydrolysis, we get kind of the base part of it back, which is the amine, and we get a salt left over. Any questions on those two there? So here again, if we look at this, this is the base hydrolysis. So again, in the base hydrolysis, we're going to get the base part back, which means this guy again is going to take the hydrogen and be completed. And once again, we are left with the carboxylic acid salt, which is the oxygen connecting in. And again, it's not the sodium connecting in here, it's the oxygen connecting in, because remember, a carboxylic acid looks like this. So a carboxylic acid salt has the oxygen connected in like this. So that's why, again, the oxygen comes in there in that particular case. Again, the base, one way you can remember it is that you get kind of the base part of it back, which again is that sort of amine group. All right, so since you don't have to worry about amides and drawing them, you don't have to worry about those. So to finish up here in terms of amides, just so we're clear, you do need to know, obviously, the functional group. You need to know some of the properties of amides. You need to know the acid-base hydrolysis reaction we just looked at, and no naming. For amines, you need to know, obviously, the functional group. You need to know the common name way of naming amines. You need to know how to draw them like we did in a couple of examples, and the sort of acid-base reaction that amines undergo, and obviously how you make an amine and how you make an amide as well. Any questions on what you need to know from these guys? Well, that wraps up officially the organic chemistry and the two nitrogen groups. And also officially wraps up the course as well. So as I mentioned earlier, again, our final is 1 week from today, starts at 4:45, does cover everything. Obviously, if you have any questions, you can feel free to email me in the next week. Clearly, we don't have class on Monday as it's finals week, so we just obviously, you will show up and take your final on Wednesday. Other than that, again, I hope you enjoyed the class and you learned something. And if you still have questions on something, I'd be happy to answer them. Otherwise, good luck on your finals. Have a good rest of your evening.